Welcome to Server-Lie, where ideas collide. In a world of tech, come take a ride. Artificial minds with hearts so bright. Join us on this journey, we're taking flight. With every bite, we're here to explore. Unlocking secrets, let's open the door. Server-Lie, let's make the magic flow. From data to dreams, we'll watch it grow. So grab your headphones, come join the fun. In the world of AI, we're never done.
Large language models, they're really the engines driving so much technological change right now.
Absolutely. Huge impact.
But you know, if you've used them for serious research or maybe complex queries, you've definitely hit that paradox.
Oh, yeah.
They get some things amazingly right, maybe generating complex code or summarizing a huge document.
Incredible stuff sometimes.
But then they get other things very interestingly wrong, and often quite confidently wrong.
And that confidence when it is wrong, well, that can be far more misleading than if it just failed outright. It's a pretty foundational problem.
It really is, which means researchers needed, well, a foundational solution.
Exactly.
Absolutely. So today, for you listening, we're cutting through the jargon, the complexity, and diving into the main framework that's designed to fix those specific LLM flaws.
The goal is really to make them more accurate, verifiable, and critically current.
We're doing a deep dive into Retrieval-Augmented Generation, or RAG. You've probably heard the term.
Yeah, RAGs become central. Our goal today is to give you a real shortcut, a way to understand why RAG isn't just some buzzword.
Right.
It's actually the engine powering pretty much all trustworthy enterprise-level LLM applications you see today.
Okay, so let's unpack the core problem first. Let's look at the default behavior of a pure generative model on its own.
Good starting point.
Let's start with the main challenge facing any model that only relies on its training data. We actually have a great little anecdote that shows both primary flaws at once.
Okay, picture this. It's a common kind of query. A user asks the model, in our solar system, what planet has the most moons?
Simple question, seems straightforward. Now, if that LLM is running purely on its internal parameters, the weights, the knowledge it got during its initial training,
which might have been months or even years ago?
Exactly. It's going to access what was the standard answer for a long, long time.
So it might reply, very confidently, Jupiter, with 88 moons.
Which sounds right, historically speaking.
Right. It was, right, for a while. But that's a textbook answer based on data captured way back at the point of training. And right there, that's the first core challenge. Currency, or rather lack of it.
Because space science, well, unlike ancient history maybe, it moves fast. Super fast. Astronomers are finding new moons kind of constantly, it seems.
They really are. So that reliance on static embedded training data means the model is immediately fundamentally out of date when it deals with dynamic information.
So what is the right answer now?
Well, if you look it up right now on a reputable current source, say NASA's website, the answer is totally different.
Okay.
The verifiable, up-to-date answer is actually Saturn, which currently boasts, I think, 146 confirmed moons.
Wow, 146. Big difference from 88.
Huge difference. So if the model is only speaking off the top of its head, from its original training data, it just cannot possibly keep up with dynamic stuff like moon counts or stock prices or recent legal changes.
Got it. And this flows right into the second problem, which feels maybe even trickier, the lack of grounding. Like if you or I give that wrong answer, Jupiter, 88, we might be confident and maybe say, oh, I'm sure I read that somewhere, but we can't point to a source supporting that claim right now.
That mirrors the LLM behavior perfectly. The model is, it's an extremely gifted pattern matcher and interpolator.
Yeah, it sounds convincing.
Totally. But without external real-time sourcing, it's prone to what we call hallucinating, essentially making up a factually incorrect but syntactically believable answer based only on its internal pattern recognition.
It generates text that looks right, but just has no verifiable foundation.
And that confidence without evidence, that's probably the biggest barrier to trust and adoption in serious applications.
Okay, so if relying on that internal static memory is the core issue, how does RAG change the game? How does it change the model's fundamental behavior?
That brings us to the retrieval-augmented part.
The R in RAG.
Exactly. Retrieval augmentation is that absolutely critical grounding step. It fundamentally changes the instruction the LLM follows. It basically says, hold on, Before you generate any response, you first must go and retrieve relevant information about the user's query from an external dedicated knowledge source.
An external knowledge source,
Okay.
okay. And the sources we looked at call this the content store. Now, this isn't just pointing it at the whole internet, is it? That sounds messy.
Crucially, no. Although it can be open, like accessing common knowledge databases or even the dynamic web for some applications.
Okay.
But where ARD becomes truly indispensable, especially for you listening in an enterprise context, is the closed store.
Right. Let's pause on that closed store idea for a second.
Yeah.
Because this seems like where the real power shift happens for businesses or specific domains.
Absolutely.
This store could contain, what, proprietary research, internal company policies,
Yeah.
technical manuals, stuff the base LLM was definitely never trained on.
Exactly right. Think about how that changes things for, say, enterprise use. Imagine a new employee needs to understand a complex, maybe 100-page internal safety manual they've obviously never read.
Asking a normal ChatGPT about that. Useless. It doesn't know the document.
Precisely. But with the RAB system that's grounded in that closed store, that specific safety manual, they can ask the model a very specific instantaneous question, like what are the reporting procedures for equipment failure in Department D? And it should provide a grounded answer, potentially even with citation lines pointing to the exact page and paragraph of the manual.
Okay, that's genuinely useful. That retrieval step, then, that's what turns the old Jupyter answer into the current Saturn answers.
Yeah.
Giving the model a real-time, up-to-date cheat sheet right before it has to answer the exam questions.
It is, essentially. But hang on, this raises a really practical engineering question, one you might be thinking about.
Go on.
If that content store has thousands, maybe millions of documents, how does the LLM know which, say, 3 documents or paragraphs to retrieve? It can't possibly scan every single page for every single query, right?
Yeah, good point. If I ask about moons, it shouldn't waste time reading the company safety manual. How does the system target the relevant info so precisely and crucially quickly?
Ah, okay, so that's where the technical magic under the hood of Auriga really shines. This is where we get into things like vector databases and embeddings.
Vector embeddings? I've heard of those. Numerical representations of meaning?
You got it. When you submit your query, Auriga doesn't just do a simple keyword match like old search engines. The system converts both your query and all the documents, or chunks of documents, in the content store into these numerical representations, vectors, or embeddings. And these vectors capture the semantic meaning, the concept of the text.
So it's not just scanning for the word moon, it's scanning for the concept of current planetary satellite count or something like that?
Exactly. The system then uses specialized, very fast search techniques to find the vectors from the content store that are conceptually closest, mathematically speaking, to the query vector.
And this is the retriever component doing its job.
That's the retriever. It pulls maybe, say, the top 3 or 5 most relevant chunks of text. We call this the context.
Oh, okay, that clarifies the retrieval part really well. Now, how does the model actually use that retrieved context to generate the final answer, the generation part of a RAG?
Right. Let's walk through the flow. In a plain old generative model, the prompt is just your question. Simple.
User asks model answers.
Yep. With RAG, the final prompt that the generative model, the G part, actually processes, it's really a composite. It has 3 essential parts put together.
Okay, 3 parts. The first part is just the original user's question, obviously.
Right. What planet has the most moons? Then part 2 is a very explicit instruction given to the model.
Like what?
Something like, answer the following question only by using the data provided in the third part below. If the data provided does not contain the answer, state clearly that you cannot answer based on the provided information.
Ah, okay. Force it to use the evidence. And the third part then is?
The actual retrieved content itself, those key paragraphs about Saturn's moons pulled from the NASA database, or those specific procedures from the safety manual.
And that retrieved content gets stuffed directly into the LLM's working memory, its context window.
Exactly. It's inserted right there. And that is the crucial difference, because the LLM is now generating its text based on this prioritized external evidence.
It can give a better answer.
Not just a better, more accurate answer, but it can actually point to the source. It can provide the evidence for its response, sometimes even citing the document or page it came from.
This mechanism, it seems to provide really elegant fixes to those initial LLM problems we talked about. Let's start with the currency, the out-of-date data issue.
Yeah, the fix here is wonderfully efficient, actually. If scientists discover even more moons around Saturn next week.
Which they probably will.
Possibly. You don't have to go through the massive time and expense of completely retraining the entire foundational LLM. That can cost millions and take weeks or months. You simply update or augment the data in that external content store. Just change the text file or database entry for Saturn's moon count.
And because the RE system is told to query that store every single time.
Exactly. The next user who asks about moons automatically gets the latest info. The model effectively stays fresh without the huge cost and delay of constant retraining.
Super practical. Okay, what about the second fix, the sourcing and the hallucination problem? How does just adding external text stop it from making things up?
Well, it relies heavily on that prompt structure and context window prioritization we just discussed.
So how does inserting that external data prevent the model from dipping back into its original, maybe incorrect training data?
Because the retrieved data, the evidence, is inserted right into the prompt, into the context window.
Yeah.
It becomes the most immediate, the highest priority information for the model to pay attention to.
You're basically telling it.
You're effectively instructing the model. Look, ignore whatever conflicting stuff you learned months or years ago during training. This verified information I just gave you is what matters right now.
So it shifts the model's focus away from its internal guessing based on old patterns.
Precisely. It directly addresses hallucination by grounding the generation in provided facts.
But hang on a sec. What if the retrieved data itself isn't perfect? If the retriever pulls slightly flawed info, couldn't the model try to blend that bad external data with its own internal knowledge? Couldn't that just create a new kind of weird hallucination?
That is the exact engineering challenge researchers are wrestling with right now. It's a major focus.
Okay.
That strict instruction only use the provided data is specifically designed to minimize that kind of blending. But you're right, it's not foolproof if the retrieved data is poor.
So it depends heavily on the quality of the retrieval.
Hugely. But REC enables another really powerful positive behavior that helps here too. Knowing when to say, I don't know.
Which we're just not used to with LLMs. They seem programmed to always answer something, even if it's total nonsense.
Exactly. RG gives the model an explicit out. If the content store, which is the single source of truth it's been instructed to use for this query, cannot reliably answer the user's question,
Then what?
then the model should, based on its instructions, refuse to answer, or state clearly that the provided information doesn't contain the answer, rather than making up something plausible but misleading.
That kind of restraint, that feels critical for building user trust, especially if you're using this for, I don't know, financial advice or medical queries.
Absolutely critical in high-stakes environments.
Okay, so we've laid out the incredible power and elegance of RE, but you mentioned trade-offs and the potential for bad retrieval. If the whole system hinges on that initial retrieval step, what happens when that part messes up?
Yeah, this is the other side of the coin, and it's where a massive amount of current research is happening. If the retrieval mechanism itself, the part turning the query into a vector and finding those conceptually relevant documents isn't good enough, well, we run headfirst into a classic garbage in, garbage out problem. GI go.
Meaning if the retriever component pulls the wrong paragraphs, maybe it grabs stuff about Jupiter's atmosphere when the user asked about Saturn's moons.
Right, or maybe it pulls outdated safety procedures.
Then the generative model, even if it's a brilliant language generator, is forced to create its response based on faulty, irrelevant evidence.
That's exactly it. In that scenario, a perfectly answerable question might fail to get an answer because the context was useless. Or worse, it might generate a confident-sounding but wrong answer, simply because the LLM was diligently following its instructions to rely only on the poor evidence it was fed by the retriever.
So this is why researchers aren't just focused on making the core generative models, the LLMs themselves, smarter and bigger.
Not at all. They must also focus intensely on making the retrieval mechanism itself smarter, faster, and more accurate.
Two sides of the same coin.
Absolutely. Current work is pushing hard on both. Improving the retriever, using better embedding models, smarter chunking strategies, more sophisticated ranking to ensure it pulls the absolute highest quality, most relevant, concise data.
And on the other side,
And improving the generative part so that when it does receive good data, it crafts the richest, most helpful, most accurate final response for the user, while crucially ensuring it never deviates or hallucinates beyond that provided source material. It's this constant iterative loop of refinement between retriever and generator.
Makes sense.
So maybe to summarize the core takeaway from this deep dive for everyone listening, RAG is really the essential mechanism that takes these incredibly fluent, highly confident, but often internally static LLMs.
And grounds them.
Exactly. Grounds them in dynamic, verifiable, external data. It tackles those core issues of data currency and confident, unsourced hallucination head on. And it does it without requiring constant, incredibly expensive retraining of the massive underlying model.
And knowing this is vital, right? Because it helps you understand how the most powerful, the most advanced LLM applications, especially the ones using, say, your own company's private data or specific domain knowledge, can actually provide answers you can trust.
They aren't just pulling information out of thin air. They're actively retrieving it from an authenticated current source that you control or trust.
That connection to evidence really changes everything.
It really does. We started by saying standalone LLMs are often very confident, even when they're dead wrong. With RAG, we fundamentally shifted the balance of power. We're forcing that confidence to be earned through verifiable evidence.
That leads to a really interesting final thought, doesn't it?
I think so. How will this fundamental shift change what we as users value more in our AI tools, in our digital assistants?
Do we want the fastest, most definitive sounding answer, even if it might be slightly off or lack sourcing?
Or do we value a response that's maybe slightly slower, but is honest enough to know its own limitations, admit when it can't answer from the provided data, and crucially, can cite its sources?
That's definitely something to think about the next time you ask an LLM a really challenging question. Which kind of answer do you truly need?